Hey folks, so in this video we're going to get into a few of the kind of picky details of data types and arithmetic expressions in Java. There's a few, it's just some details we have to go over really. You guys know most of what I'm about to say, probably at least the concepts behind it from your Python course. But Java treats data, each language treats data types in its own way. So we have a few little topics that we have to look at here. So let's take a look at the guide here. So we're in data types and expressions. There's a few things to point out right off the top about data types. So you already know that if you don't declare something, if you don't declare a variable, you can't use it. And you are restricted when you declare that variable by the type. So this is already different from Python. We covered this in the first video. It's static typing versus dynamic typing. There's a few other issues as well with how Python treats both literals and conversions between types. Java has, I think, more primitive types in it than than Python does. It's got 8, so we're going to take a look at all those. But a few things to say first. In Python, you can do this. You can you can have an integer as big as you like. You can do 2 to the power 10,000 in Python, and it's got no problem with it. Java, integer types, and there are actually 4 different integer types. They all have a size limit on them. Okay, so this is a case of sacrificing convenience, which is what you get with unbounded integers, for performance, which is what you get when you have bounded integers. So in Java, integers can only go up to a certain value because we only have 4 bytes in which to store the integer. So we use 2's complement representation inside the machine. I think you guys learned about that in computer math, which means that we can go into positives and we can go into negatives, and it dictates for 32 bits what the highest possible value and the lowest possible value are. And I don't know if you remember about 2's complement, but there's always one more negative value than there is positive value. So this, for example, is not allowed. And if you go over, let me start a new piece of code here, new package for data types like that. And then I'll just create a new class in here. I will call it data type examples. I don't think it's going to be particularly exciting code today. Just some not as exciting as graphics. Coming off of graphics, I mean, not maybe that excited you, maybe it didn't. But this is maybe in some ways less exciting. But here we go. So if you have an integer variable a, you can store, reasonable sized numbers in it. If I go system.println a right now, that should compile and run no problem. I think I have to do Control-Shift-F10 to get it to run the first time, and then I can use the play button over here. So there you go, no problem. But there's a maximum. If I add one more digit to this, I'm over the maximum. Integer number too large. Okay, so I can only store up to positive and negative, the maximum number I can store inside of 32 bits. This is not maybe a little off the beaten path, but every primitive type, every type that starts with a lowercase letter like this, like int and double, has a corresponding class with a capital I. So capital I integer, and this is where they put a bunch of kind of useful constants and useful methods and things like that. They go into these classes. So integer and double and a bunch of other types have this max value. So if you want to know what's the maximum value, you can do this. You can print it out like that. So there's your maximum possible integer value, and your min value is going to be, remember that number. This is the highest positive integer you can get in 31 bits, I think, because there's a sign bit at the front. And if we run this again, you notice the magnitude of this is 1 greater, but it's negative. So you have a minimum and a maximum value. And you can overflow them. Like if you have the max value, if you're already at the maximum value of your integer, and you go a equals a plus 1, let's do a printout here. Print it here, and then add one and print it again. I don't know how much you remember about 2's complement, But if you add 1 to the maximum value in 2's complement, it flips all the bits over. So you end up with, instead of 0, 1, 1, 1, 1, 1, 1, you end up with 1, 0, 0, 0, 0, 0, which happens to be the way that 2's complement encodes the smallest possible number. So you have this situation where if you overflow an integer, it's like rolling the odometer on your car. It goes back to 0, or in this case, it goes back to negative. So when you're doing arithmetic calculations with large numbers and you start to get weird results and negatives where you don't expect them and stuff, there's a good chance that you are overflowing the maximum size of an integer. So what do you want, really? You want not an int, but a long. So long is a long integer. These longs are 8 bytes. So if you know that you're going to go over the 2 billion, or whatever this is, yeah, it's 2 billion, 2.1 billion, long gets you much larger numbers. So if I do the same thing, if I assign the maximum value of an integer to long and then add 1 to it, you'll see that it's no problem. It can handle it. If we change this to long to see what is the maximum value of a 64-bit 2's complement integer, you'll see the same overflow. But you can see, as you can see, the numbers get much, much larger here before they overflow. Okay, so those are 2 basic integer types that you might actually want to use. The default is int, but if you need bigger numbers, you can use long. If you want bigger numbers even than this, there is an unbounded integer type called big integer inside Java, but it's a class, so you're no longer dealing with a primitive value. So let's talk a little bit about, so let's just recap a little bit. There are 2 types of, there are 2 data types, two data type forms, 2 basic kinds of data types in Java, primitive and object. Okay, primitive data types just store a single value, and the biggest primitive data type I think is 8 bytes long. So the long integer is 8 bytes, and it stores an integer using those 8 bytes. Int is 4 bytes, and so on. These are just single values stored in memory in a contiguous set of bytes within RAM. Then you have these object types, and you can usually tell object types like string because they start with an uppercase letter. Objects contain a whole combinations of primitive types. So the primitive types are the building blocks that objects and classes are built out of. So the string object, for example, is basically a list of character types, char types. So there's this other type built into, where are we? Here we are. So that's integers. Let's take a look at char types. If I go char c equals, a character is just a single letter like that. So that is a primitive type. Notice it starts with a lowercase there. I can do system out print line. Whoops, I did printf there. There we go. I can print out that character, and it'll just print an E. I cannot put more than one character inside these single quotes. That's another difference from Python. Python doesn't care whether you use double or single quotes. In Java, single quotes are for characters, which are a single type. They're 2 bytes long, and the character C is just the Unicode value that goes along with that. So every character that you can print on the screen has a number that goes with it. And if you put an int in brackets in front of the variable C there, you can actually see the Unicode value. So you can see that the Unicode value of lowercase e is 101. So a string then is an object built out of a list of these char types. And it also adds a bunch of methods and things that you can call and so on. So the primitive types in Java are the basic building blocks. There's a few more. What have I done here? I've shown you that you have this char type which doesn't exist in Python. If you use single quotes, you just have a single length string, a string of length 1. String types use double quotes in Java. Char types use single quotes. So this is a syntax error here. You can't put the word hello inside single quotes. That's not a string. The single quotes indicates a character, so you can't put more than one thing in there. Okay, now let's take a look. There are 8, like I said, there's 8 primitive types in Java, and they're listed in section 2.1 of the textbook. And what I've done is I have, over here in the first module, I've scanned a couple of pages for you. So just in case you don't have access to the textbook, if you go into here, primitive types and strings, there's 2 pages here. The first one we're just going to look at now. shows you the 8 basic types. So these are the names of them. So we've just covered int. It's an integer. It uses 4 bytes of memory, and this is the range of values it can store. Long, we also looked at, is an integer type, but it's 8 bytes long. So you can use that. And then the other one we've seen before here is double, which is a floating point number. With doubles, with floating point numbers, they can go into scientific notation. So the highest number is 1.8 approximately times 10 to the 308. So 1, 8, and then 307 zeros. And as you can get really, really big and really, really small numbers, so positive or negative, and really small numbers. So this is times 10 to the negative 324. So it's 0.0323 times 4. What you're limited in when you're using floating point numbers is precision. So we have, I think, about 17 digits of precision here. And there's a smaller format called float, which is a floating point number also, but it's a 4-byte system that only gives you 9 digits of precision and doesn't let you go as high or as low. So typically the default types here are int and double for numbers, but people use long when they need to get a bit bigger. There are also integer types that are smaller. So for example, there's a type called byte. B equals 23. This can store a single byte of information. So if it was unsigned, it would go from 0 to 255 because there's 8 bits. But it is 2's complement, so it goes. The maximum number is 127. If you go to 128, you have an error, and the minimum number is negative 128. And if you go smaller than that, you also have an error. Okay. There's also short, which is a 2-byte type, so goes from 32,767, I believe. If you go higher than that, you have an error. That's a 15-bit number, biggest positive 15-bit number, and you can go to negative 32,768. Anything below that is going to be an error. Generally speaking, we don't use these. The only time you would ever want to use a byte, like let's say you were storing small numbers, like they're always from 0 to 10, it's a bit of a waste to store it in an integer. You don't need 4 bytes to store numbers that big, but it doesn't really matter most of the time unless you're storing 10 million of those numbers. And then it makes a difference whether you're using 10 million or 40 million bytes. So that's when you might use a byte or a short if you're storing like a big data structure, a big array or list of those numbers. Otherwise, it's good to know that they're there, but we don't really need them. The ones we do need are int and long. There's a couple of caveats here. If you create a long integer, let's call it L. So let's say I want to give it a really big value. I know that the biggest number I can get in an integer is about 2.1 billion. So 2 million billion. Oops. So that works. But I want to make a bigger number. So I go like this, and suddenly I have an error. Integer number too large. The reason why this is an error is because by default, when you just type a number into this, when you type what's called a number literal, it's going to be of type int. There's something special you have to do. If you want to type in a really large number and assign it to a long, you put the letter L after it, and then it works. So this will work now. It'll print out that long. So if you want to do literals like that, and it goes the other way for doubles and floats. So if you go double D equals, whatever, some number like that, that's fine. Float F equals, oops, not doing this very well. There we go. And this is not float, this is float. This gives you an error right off the bat because by default, this when you type a decimal number in, it's automatically a double unless you tell it that it's a float. Just like with integers, it's automatically an integer unless you tell it by putting an L on the end that it's a long. So if I want to specify that I want this stored as a float, I have to put an F after it. But again, we don't usually use floats unless space is a concern. If we know we don't want, floats give us about 9 digits of precision, double gives us about 17. If we know that 9 digits of precision is enough, and we're storing 1 million values, maybe we want to use float. But it does cause a few little headaches here. Okay, so those are your basic numeric types. There are 6 of them. There's double, there's float, long, byte, short, and int. Let's make this go back to int, like that. Okay, so those are your 6 basic numeric types. Let's put a little comment on here. And then there are other types. There's characters. Here's the character types here. Put this over here. And that's number 7, and number 8 is the Boolean type. So you can create a Boolean variable, b equals, and there's 2 possible values, true or false. I think I've already used b. Call it flag. And you can do stuff like, you can print it like that. If you run that, it should, the last line out of here should be true. You can do logical operations. So exclamation mark negates it. So not flag is going to be false, and so on. We'll deal more with the Boolean type when we get into next week, when we get into if statements and loops and stuff like that. Okay, so those are the 8 basic types. Okay, so yeah, we will mostly use in this course ints, doubles, and strings. You might occasionally dip into chars or booleans. If you want to do large numbers, you might need to go into longs and so on. Just be aware that there's a few little gotchas, like using the letter L and F to convert. Okay, so those are your primitive objects. Then there are primitive types. Then there are object types, and there are thousands and thousands of them. The 3 that we've seen so far are string, scanner, and graphics context. So graphics context, if you think of it as a 2-dimensional array of pixels, so it's built out of hundreds or thousands of individual doubles or ints, or however it represents itself. And graphics context also contains a bunch of methods that you can call, like fill rect and so on. Scanner as well, next int, next line, and so on. And it somehow stores the contents of the keyboard buffer inside of it. Okay, so those are your types. Arithmetic expressions. You guys already know about arithmetic expressions from Python. There's just a few little things that I have to tell you about. The first one here is that when you're doing division, we don't have, so Python had a double slash and a single slash. I don't know if you will have seen this, but try it in Python. Double slash is integer division. So if x is 5, x double slash 2 gives you 2, because 2 divides into 5 2 times with some remainder left over. The regular division, even though x and 2 are both integers, will give you 2.5. We'll answer a double. That's not true in Java. So the way Java works is if I go system out println 5 divided by 2 like that, because this operand and this operand are both integers, the answer will be an integer. So see, it answers 2 here. If I wanted to get that, if I wanted to make that into a double, I have to make one or both of these operands a double. So just adding 2.0 here means that this is a double, and that changes things. So what Java's looking at this now and saying, well, they want me to divide an integer by a double. Those 2 representations of numbers are totally different. So the only way I can do this is if I convert. And I can't convert a double to an integer because I might lose precision. I might lose the decimal point, but I can more easily convert an integer to a double. So it converts the int to a double, and then we get division using doubles, and the answer is a double, 2.5. The other way to accomplish that is if I have an integer variable, so up here I have this integer variable a, which is set to the max value, which is this, which is an odd number. Right, so if I go system out println a divided by 2 like that, it's going to give me give me back an integer. Oh right, let's go a equals like that. Make it odd. There we go. So now it's going to give me back instead of, this is an odd number, so it should give me 0.5, but it doesn't. If I want to convert that, I can either go 0.0 here to convert that to a double, but the other way I can do it is I can put the keyword double in brackets in front of the thing that I want to convert. So let's take a look at this. What's actually going on here, let me go Alt-Shift-L. Nope. Alt-Control-L? There we go. So what I'm doing here is I'm saying the thing beside the double operator here in brackets, turn that into a double if you can. So I'm telling it explicitly, turn this into a double and then divide it by 2. And that will have the desired effect as well. That'll get me the 0.5 that I wanted. Okay, so this is called casting. And there's a lot of casting that goes on behind the scenes. There's a lot of what's called implicit casting. So conversions that the system does for you. If I have a double variable called x and I set it to 45, well, I'm trying to assign an integer to a double, but that's okay. So this is implicitly cast. It converts this integer to a double and stores it in x. But if I try to go the other way, like that, that's an error. That's a syntax error. It cannot implicitly cast that, or it won't do it, because it knows if it does that, it's going to lose precision. It's going to have to do something about the 0.5, either drop it or round it up or something like that. And it won't even let me do 45.0. It just won't. That's the way Java works. You cannot automatically convert from a double to an integer. I can force it to convert like this. So that's explicit casting to an integer. Okay, and when I do that, it's going to just drop off the decimal place for me. So if I go system out print line y here, it's going to drop off the decimal and just print out 45. Okay, there's also implicit casting that goes on whenever we do this. Y is now plus y. I don't know if you noticed this, but in Python, casting in Python was done like this. It was a little function that would convert that to a string. You don't actually have to do that here. Plus means addition, but it also means concatenation. So if it sees two numbers on either side of the plus, it will do numeric addition. But if one of them is a string, it converts the other to a string and does concatenation. So that's how this works, is through implicit typecasting. So implicit casting to a string. All right, I hope that makes sense. Where are we? Yeah. So yeah, the double slash doesn't exist. What matters when you're doing division in Java is whether you have integers or doubles on either side of the division sign. That depends on what you get. And of course, you also have the modulus operator, which you can do like this. So system out print line a modulus 2. That should print out 1, right? Because it's an odd number. So that's going to print out 1. Modulus works just like it did in Python. Hopefully you saw that in Python. There it is right there. So it's the remainder after doing the integer division. What else? This is concatenation. This is something, I don't know if you ever saw this, but in Python you can multiply strings by numbers, and it basically concatenates the string together that number of times. You can't do that in Java. In Python, you also have the double asterisk, which is the power operator. So this is x to the power 2. There is no such operator in Java, but there is a class called math that contains a bunch of methods that let you do things like that. So math.pow raises this to this exponent. And the thing about math.pow, though, is that it always returns a double, which is why I had to do the integer cast here. So if I just copy this for a second, Control C, and I'll just put it over here. I think I've already used the variable c, though. Yeah, I can't redeclare that variable, so I'll call this one power. Math is one of those classes that's already in the system. If I just print this out, what's x? Oh, x is actually a double. So this is going to give me 45 raised to the power 2, which is going to be what? 1600 plus some. So yeah, 2025. Without the int casting, this would have just gotten me. What did I just do? Oh, I got an error here. Oh, because I'm trying to store it in an int. Okay, so that's important. So you see that error there? It's saying required type int provided double. So this is actually returning a double, and I'm trying to store it in a variable of type int. But this should fix it. There we go. Now it gives me the same number with a 0.0 on the end. The math class has a whole bunch of stuff. If you just go math dot, you can see, so pow for raising to exponents, absolute value There's cosine and tan in here as well. There's cosine. Rounding methods are in here. There should be a round method here. Round. And notice there's multiple versions of them. You can round off a float or a double. Rint rounds to an integer, but for some reason always gives you back a double. That's a weird one. This is what you're seeing over here is the return type. So if you go math.round, 23.432, system out print line that, Alt-Shift-L, that will print out 23 because it's going to round down. There it is right there, 23. But if I make this 0.5 by the regular rounding rules, it will round up to 24. And notice, you can tell it's an integer because there's no 0.0 on it. So there's tons of stuff in the math class. You can also find out more about the math class if we go into the API. So last video I took you into the JavaFX API. So that's in the resources section here. We went here. There's a second API document for the base Java classes. And if I just search here for math, java.lang.math, and you can see there's a couple of constants in there for e and for pi. So math.pi uppercase returns an approximation of pi. And then here's all the different methods that you can use. When we're doing random numbers, we're going to use math.random a lot too. That's not the only way to do random numbers in Java, but it's the way that I like the most. Square root, hyperbolic sine, you can do all kinds of stuff here. All kinds of useful stuff in the math class. And let's do a system out print line of math.pi as well while we're at it. There it is. So that gets you a double representation of pi, which should be about 17 digits or so of pi. Okay, I think that's everything. Just go back and take a look here. I talked about casting, and sometimes automatic casting can be done, and sometimes it can't. So you can't. The big one is you can't cast a double to an int automatically. You'll have to do that yourself. Here it is. To convert types in Java, put the name in brackets. Put the type name in brackets in front of the expression. This is known as typecasting. So that's what's going on here. This is all covered in the section as well. Oh, and one last thing I should talk about is named constants. Notice that pi is in uppercase here. That indicates that it's a constant. You can't assign to it. Math. So a constant, I'm not sure if Python has constants. But you can't do this. Cannot assign value to a final variable pi. So you use constants when you want to do things like, say, compute the tax. So if you have a variable, like a number like 0.13, I think that's the current sales tax. It would be 13%. And you've got a financial app, so you're using 0.13 everywhere. And then they raise the tax to 0.14. Now you have to go through all your code, find all the places where you've done 0.13 and change it to 0.14. So the obvious thing to do is to not do that, to store it in a variable. So you could have a double variable called tax rate, which is equal to 0.13, like that. But just having it as a variable like that is a bit difficult because a user might change it later. Tax rate equals, you might accidentally use that variable to do something else, and then your app is broken if you're accidentally changing the tax rate somewhere. So what people can do is they put this keyword final on there, double final tax rate. I think it's final double tax rate. There we go, that's better. So you put the keyword final in front of the type, and this means that once this is assigned one time, it can't be assigned again. So this becomes an error, cannot assign value to final. Now this is a handy thing to do. A lot of people would say that other than x plus 1 and things like that, you shouldn't really have any numbers in your arithmetic expressions. So you shouldn't be doing, double amount equals, 23 times 0.13. What you should be doing is price times tax rate. It makes things easier to see It makes it easier to understand this expression. So it's good from a code documentation point of view. And it's also good for tax rate, not tax rage. Tax rage is something different. Something we experience every year in April. Unless we're getting refunds, which probably most of you are. So this, it also enables you to, if the tax rate goes up, you only have to change it in one place. So the tax rate goes up to 14%, you just change it here. So there's a lot of people who think that from documentation point of view, this is what your code should look like. Now the one last thing is that when people make constants, there's kind of an unwritten rule. Not everybody uses this. There's kind of a bit of a debate, but I think most programmers would use all caps for a constant, just to make it clear when you're reading the code that what you're looking at here is not a variable but a constant. It's a final variable. So use all caps and separate words with an underscore. And we've seen that before. When I go color dot, these numbers here, notice how they're all, Burleywood was in all caps. That's because it's a constant. So Java uses that convention everywhere. Okay, so just a bunch of disconnected examples there, but it is going to be an expectation of this course that if you're using a constant throughout your code, if you're using a number throughout your code, that you really should declare it as a constant up here, name it in all caps, and then use it throughout your code. That is, I think, everything that we need to look at now. And I want to leave you with an exercise that lets you use this stuff. And the exercise I'd like you to do is this one here. This exercise kind of sets you up for the assignments that are to come and for stuff that's coming soon. Because I want you to do some calculations, but I want you to do it inside of the FX graphics template. You can do this one, or if that one looks too long, you could always do this one as well. Maybe we'll focus on this one. It's just an input processing output program. The user enters Canadian dollars and you convert it to some other currency. So you ask them to enter the amount, say, in Canadian dollars, then you display the equivalent amount in the other currency using JavaFX graphics. So the idea is that you display that like in a nice font with a dollar sign, maybe a thick line underlining it, or whatever. I think I have week 1 solutions. I think there's a solution for this one. Might be exercise 4C. Let's see if it's exercise 4C. So I'm going to copy this and I'm going to put it over here, in here. Okay. Let's not look at it. Let's just run it, because I want you guys to work it out on your own. Is this what I think it's going to be? Yeah, enter an amount in Canadian dollars, 45.50, and it's converted it to, looks like British pounds or euros or something like that. It looks like British pounds. So it's saying $45. And notice I've put it in a very small little graphical window. So the idea here is that you do your dialogue with the user in between where it says put your code here. So over here you put your dialogue here, you create a scanner, you do your dialogue, then you do your drawing, and at the end it ends with stage.show, which pops up the window and shows you the drawing that you did. And if you can do that, that's going to put you in good shape for doing the first assignment, because that's kind of the structure of the code. Okay, I think that's everything for today. Yeah, so I'll leave you with that exercise. Yeah, so you can do this one if you want, which is converting a grade from the course, but maybe this one's a little bit quicker to do. And what I want you to do here is figure out, if you can, figure out how to round the answer to 2 decimal places. That could be a little bit tricky, but see if you can figure it out. And we can talk about that in the live class if you want. Other than that, I will see you. We have one more video. I think it's going to be a short one, I hope, fingers crossed, on strings. And then I will see you in the live class at the end of the week.